So this question, we are going to think about what happens when I have several objects, and these objects you'll notice are attached together. So I kind of have to think about that scenario. Now you'll notice that I have three carts, all with different masses. And what I'm trying to find is the force on each of the strings that are involved here. And I know the overall force being applied because it's saying it's a child pulling this and that's causing these three things to move. So I kind of have to think about them as separate entities, but also as one entity. Now, to make this a little easier, just for following along the math, and I highly suggest you do this kind of thing, I'm going to call them A, B, and C just to make it a little easier for you to follow the math. And you want to do that kind of thing because someday I'm going to be marking your math and it would be good to be able to understand what you're talking about. And I'm going to call this force one, the force on the first string, and this one F2 or the second string. It doesn't matter what order you do them in. I'm doing them in this order because I'm going to actually solve from the back to the front because it's actually less complex that way. And then what I'm going to do is I'm going to think about each of these objects. So if I think about this object as a separate entity, you will notice we're assuming no friction. We will do ones with friction as well, but we're going to start with no friction just to simplify at the start. And you'll notice that means if there's no friction, all that's happening to this one is F1, force 1, is pulling forwards on this cart, right? It does have a normal force and a gravity force. So that would be its free body diagram. If I think about this second object, it's a little more complex because it's being pulled forward by F2. But you'll notice equal and opposite reaction. So whatever pulls cart A forwards is going to pull cart B backwards because they're attached. There's an equal and opposite reaction. So F2 is actually going to kind of act like drag in this case. So it's going to pull backwards because this cart is having to drag the cart behind it forwards. And by doing it this way, that incorporates the two forces. And then if I think about this front one, and we're not going to actually need to use this as much, but it has the applied force off the front that's pulling everything, and then it's being dragged by F2. Now, a lot of people would say it's F2 and F1, but I want to point out that when we think about this card, this F2 already is incorporating F1. So this force on this string already deals with the force here, so I don't have to worry about it. So this force is acting as the drag, and this one is pulling the whole thing forward. So the first thing I need to do is kind of find something they have in common, right? Because I don't know F1 and I don't know F2, so I can't really solve any of these right now. However, I do know one very important thing. They're attached to each other. And since they're attached to each other, they will have the same acceleration. That means if I consider them as an overall entity, so their overall acceleration is what I'm going to start with, because this will be handy because once I have it for the whole system, I actually have their individual accelerations as well. And that will allow me to find their individual net forces, etc. And that will let me solve that question. So I'm going to start with this. So I'm going to consider, first of all, their total mass. And their total mass, of course, is their masses added together. So that's 1 kilogram plus 1.5 kilograms plus the 0.5 kilograms. So that means a total of 3 kilograms. Excellent. And then I know that the overall or total force pulling them is the 6 newtons on the front. That's what the actual person pulling this toy is applying. So that's the actual applied force. So that means in this case, if I look at that overall idea, that the net force in this case is going to be equal to that overall applied force of the whole entity, not individual carts, the whole entity. And that means that the mass times the acceleration is equal to that 6 newtons. What this lets me do is if I put that overall mass in of 3, it lets me find the acceleration of the system, right? So the whole system, not individuals, the whole system has an acceleration of 2 meters per second squared. But that also means those individual carts have an acceleration of 2 meters per second squared, which is incredibly handy, right? That allows me to solve for them as individuals. So now I'm going to go back to cart A and think about cart A as an individual, because you'll notice as an individual, its net force statement is pretty straightforward. It has no friction, so the net force is equal to just this forwards force, this F1 pulling on it. So if we go back to just cart A, right, if I can consider what's happening in cart A, then its net force statement is pretty straightforward. Its net force is just equal to F1 pulling it forward because it has no friction. That means its mass times its acceleration will be equal to F1. And now I know its mass, right? Its mass is 1 kilogram. And I know its acceleration because the acceleration of all the carts are the same. So that means that let's actually put the number in. I didn't put the number in, I put an A in. I know what A is, it's 2. There we go, got ahead of myself there. So I know it's 2, then I could find that force 1 is 2 newtons. Excellent, no problem, right? Very straightforward. Now let's move on to object B. If we look at object B in this, it has F1 slowing it down and F2 pulling it forward. And I can now just write its net force statement. Its net force statement being that the net force moving it forwards is equal to its F2 minus F1 in this case. So its mass times acceleration is going to be F2 minus F1. I know its mass, and it's just the mass of this cart, not the whole thing, because I'm looking at the individual cart only. I'm considering it as an individual object. It has 1.5 as a mass, and 2 is its acceleration. And it has F2 pulling it forward, and F1 is slowing it down. We know F1, we found it already. So when you solve for F2, you find that it is 5 newtons, and that is what you'd put in your therefore statement.